Hi students, welcome to Vignan Digital Classes. This is S. Srinivas, Lecture in Physics, Vignan Junior College, Vadlumudi. Students, here we are talking about the magnetism and matter. Already we completed 5 videos belongs to magnetism and matter. In previous videos of this chapter, we discussed about what is meant by magnetism, what are the properties of bar magnet and magnetic field along axial line, equatorial line of a bar magnet, then followed by torque acting on the bar magnet in uniform magnetic field, then work done to rotate the magnet in uniform magnetic field, and we described about some basic definitions of magnetism such as magnetic intensity of magnetization, and then susceptibility, relative permeability. And one more important topic that we covered in previous videos are elements of earth magnetism, that is regarding terrestrial magnetism. So in this part of the video, we are going to talk about the properties of dia, para and ferromagnetic substances. We have different substances available for us like iron, cobalt, nickel, aluminum, copper, oxygen. So these substances shows their magnetic property in different ways. Depending upon magnetic property shown by the substances, the available substances are classified into 3 categories such as dia, para and ferromagnetic substances. So in this video, first of all, we will discuss about the classification of magnetic material into 3 categories and their properties, their examples and their applications. And next one, Curie's law. The ferromagnetic substances, its magnetic property changes related to temperature. How the magnetism of a paramagnetic substance is related to temperature described in this Curie's law in magnetism, that is the second content. And next one is the hysteresis in magnetism. When applied magnetizing force changes on a ferromagnetic material, especially on a ferromagnetic material, as applied magnetizing field is changing, the induced magnetism in the ferromagnetism also changes. The variation is observed in hysteresis loop. With the help of that loop, we describe which ferromagnetic material are used for electromagnet and which are used for permanent magnet. So that will be discussed in the hysteresis loop in magnetism. So these are the 3 topics that we are going to discuss. Students, in recent JEE main examinations, there were some theory questions given on the properties of dia, para and ferromagnetic substances as well as hysteresis loop. Some applications of hysteresis loop will be discussed. Already problems were given on theoretical concept also. So let's get ready to start this class. So first one is the comparison of dia, para and ferromagnetic materials. As I explained, we have so many substances that we discuss in daily life such as iron, cobalt, nickel, oxygen, copper, aluminum. So these all the substances doesn't show the magnetic property in same way. Each and every substance has its own magnetism, magnetic property. Depending upon that magnetic property, the magnetic substances are classified into 3 categories such as dia, para and ferromagnetic material. So let me first define what is meant by dia and para and ferromagnetic substances. So hence this is the definition. Diamagnetic substances are those substances which are feebly repelled by magnets. If you have a permanent magnet, then the substances which are feebly and a little amount, lightly repelled by magnet, substances which are feebly repelled, when you move any substance nearer to permanent magnet, if it is repelled feebly by the magnet, such substances are diamagnetic substances. Example, antimony, bismuth, Here these are the examples of diamagnetic substances: antimony, bismuth, copper, gold, silver, quartz, mercury, alcohol, water, hydrogen, air, argon, etc. Students, this diamagnetic property in general exists in almost all the substances. Suppose you have a copper material, copper plate. When you move the magnet towards the copper plate, that increase in magnetism through the copper is opposed by the magnet opposed by the copper. As copper have electrons, it gets circulating the electrons in such a way to produce a magnetic field opposite to the applied or increasing magnetic field, so that as these two applied and induced magnetic field are opposite, definitely the substance get reflected, that means get thrown away by the permanent magnet. So this is a in general property exists in most of the substances. Diamagnetic property in generally existing in most of the substances. So the substances which are feebly reflected by the feebly repelled by the permanent magnets are known as the diamagnetic substances. Next, paramagnetic substances. Substances which are feebly attracted. The definition is quite opposite to diamagnetic substance, quite opposite. So substances which are feebly attracted by the, here this is important thing, feebly attracted by the magnet. In previous one, feebly repelled. Now feebly, lightly attracted by the substances is known as paramagnetic substances. So aluminum, chromium, alkali and alkaline earth metals, platinum, oxygen, etc. belongs to paramagnetic substances. Substances which are feebly attracted by a magnet are paramagnetic substances. Next one, third one is ferromagnetic substances. Substances which are strongly attracted. Here this is feebly attracted, para. So compared to para and ferro, para has magnetic property in small amount and strong magnetic property shown by ferromagnetic substances. Clearly shows that substances which are strongly attracted by any magnet is named as the ferromagnetic substances. So para and ferro, both the substances shows magnetic property, but para shows lightly and ferro shows strongly. Para magnetic material are feebly attracted, whereas ferromagnetic substances are strongly attracted by the magnet. Such as iron, cobalt, nickel, gadolinium and dysprosium are some examples of the ferromagnetic substances. So iron, cobalt, nickel are the most important examples for the ferromagnetic substances. So next I would like to describe how the substances are getting, what is the difference in getting the diamagnetism, paramagnetism and ferromagnetism, what is the internal structure of these materials to have. So remember, all are metals. Copper is a metal, aluminum is a metal, iron, cobalt, nickel, all are metals, but copper belongs to diamagnetism, aluminum belongs to paramagnetism and iron, cobalt, nickel belongs to ferromagnetism. So all are metals but showing different natures. Then we would like to know what is the structure difference and nature difference to have these three different properties such as dia, para and ferro properties. So let us move on to that discussion. Here first one is diamagnetic substances. So suppose if you consider a copper, let this be a copper loop. We know that copper is a very good example of diamagnetic substances. Suppose let this be a magnet. Let this be the north pole of magnet and this is the south pole of magnet. We have a permanent magnet having north and south poles. Suppose this magnet tends to move towards the copper, the magnetic field lines through copper get increasing. But according to Lenz's law, naturally that was opposed by the diamagnetic substances. For that, it may rotates the charges, let it be positive charges along a particular direction. If suppose electrons are revolved in this direction, then positive charges are said to be revolving in this direction. Don't get confused. If electrons revolves in clockwise, positive charges are appears to be assumed to be revolving in anti-clockwise, so that this face towards the magnet becomes north pole face. So when the magnet is approaching the copper, magnetic field through the copper coil get increasing, then the copper coil doesn't allow the increase in magnetic field naturally, then it starts the electrons to revolve in clockwise, so that positive charges assumed to be revolving in anti-clockwise, so that the face of the coil becomes the north pole. It becomes a dipole. Without passing the current, the copper itself revolves the free electrons inside the copper in clockwise, so that positive charges are assumed to be revolving in anti-clockwise direction, so that face of the coil becomes north pole and it opposes the growth of flux through it, so that these two repulse each other. That's why this copper obviously feebly reflected by the magnet. In that way, this is the diamagnetic property exhibited generally by all these substances. All these substances have the nature of diamagnetism. The induced magnetism instantaneously, and that opposes the change in magnetic field through it, so that the magnetic substances are get reflected, that repelled by the magnet, hence they are named as the diamagnetism. Student, I hope you followed the nature of diamagnetism. Next comes to ferromagnetism. If you consider the substances such as aluminum is the very good example of ferromagnetic substances. So in general, when you consider aluminum, it is made up of so many atoms. Aluminum, any substance, is made up of so many atoms. In atom, there are electrons in the orbits. As electron is revolving in the orbit, so revolution of electron, if you consider that electron is revolving in an orbit, so revolution of electron in an orbit acts like a dipole of magnet, so it possesses magnetism. Due to random orientation, atoms may not be oriented in same way. Due to energy, thermal energy, definitely all substances are kept at some temperature. Due to the temperature, they gain thermal energy. The thermal energy gives the random motion of the atoms. Due to random motion of atoms, some atoms may give the dipole moment in particular direction, some may give in different directions. Different atoms contribute dipole moment in different directions, as I drawn here. Students, so some dipole moments get cancelled. Suppose these two get cancelled each other, and the up one and down one may cancel each other, and resultantly, partially, there is some magnetic movement. Resultant, partially there is magnetic movement. Resultant, partially there is a magnetic movement added up for this substance, hence they are showing a partial magnetic property, hence they are known as the paramagnetic substances. When a magnet is kept close to them, these atoms oriented in a particular direction such that they are feebly attracted by the magnet. So there is a partial net magnetic moment. So net magnetic moment of the substance is a partial. All atoms doesn't contribute resultant magnetic moment in same direction. Even though each atom has its own magnetic moment, each atom behaves like a dipole. Students, even though each atom behaves like a dipole because of revolution of electron and contribute magnetic momentum, but due to random motion alignment of atoms inside the substance, the magnetic movement of majority atoms get cancelled, and partially net magnetic momentum exists in a particular direction. So that net partial magnetic momentum exhibited by the substance shows a partial magnetic property by the substance, hence it is named as the paramagnetic substances. Next comes to ferromagnetic substances such as iron, cobalt and nickel. So for such substances, when you consider substances like iron, cobalt, nickel, they have domains structure. Here these are domains. I divided, for example, to know about ferromagnetic property, let us consider we have 1, 2, 3, 4, 5 regions. Let them be named as domains. So name of each region is domain. So each domain is the region. Each domain is the region of the substance in which all the atoms contribute their magnetic moment along same direction. So each domain is the region of the given substance in which all the atoms contribute magnetic momentum along the same direction. So here all the atoms in this domain contribute magnetic moment along same direction, like this, a group of atoms. So practically this domain may have a group of atoms equal to 10 power 11. So it is in the order of 10 power 11. Students, large number. A large number of atoms in particular region contribute magnetic momentum along one direction. This is named as the domain. Domain structures are available present in case of ferromagnetic substances. So here this second domain may contribute magnetic moment along this direction. But all the substances which are in the number of 10 power 11, in the order of 10 power 11, contribute magnetic moment in same direction. This may contribute magnetic moment along this direction. So each and every atom in a particular domain must have the magnetic momentum along same direction. So there is large magnetic momentum in first domain, similarly large magnetic momentum in second domain, large magnetic momentum in third domain and so on. Like that each and domain has its own orientation of all atoms and contribute magnetic momentum in particular direction. When this magnetic material is kept in any external magnetic field, suppose this material in which there are domains, each domain has a magnetic moment contribution of all atoms along same direction. This domain all atoms must have the same momentum, and in this domain all atoms possess the magnetic momentum in same direction. In this domain, like this, in each and every domain all dipoles, all atoms contribute magnetic moment along only one direction. When this ferromagnetic material possessing domain structure kept in any external magnetic field, all may orient along the applied magnetic field. So when magnetic field is applied, so see the image. So like that, all are oriented along same direction. See, this is the image animation that shows the orientation of domains along same direction. So first of all, there is no magnetic field. Now I applied magnetic field and all are oriented, all domains are orienting their atoms along same direction to contribute their magnetic movements along same direction. So as shown in this animated image, we clearly observe the orientation of all atoms, all domains, orientation of all domains almost along parallel to the applied external magnetic field, and it contributes large amount of magnetic field and it shows highly magnetic property, that is ferromagnetic substances. So they are very strongly attracted by the permanent magnet. So student, I hope you understood the basic difference to achieve the dia, para and ferromagnetic. This is the basic difference. I explained the basic difference in the structures to show the properties of dia, para and ferro. So let us move on to further discuss about the classification, properties of each one. Just so far I explained two things. One is the definition of dia, para, ferro and their examples, followed by the how the each one has its property. Let us move on to the next part of discussion of the classification. Here, the second property, when diamagnetic substances, when placed in a magnetic field, lines of force tends to avoid the substance because it is repelled. I shown the nature of diamagnetic substances in previous part of this session. I clearly explained there is induced magnetic field in diamagnetism that always try to oppose the applied magnetic field. Because of that reason, when diamagnetic substances such as copper placed in magnetic field, lines of forces tend to avoid the substance, trying to move away, try to move outside the substances, whereas lines of forces prefer to pass through the substance. And here the lines of forces tends to crowd into the specimen. Here crowd, we are using the term crowd because it shows a strong magnetic property. Here lines of forces just passes through the substances, whereas in ferromagnetism the magnetic lines of forces tend to crowd. So I feel you understand this explanation effectively by using one animation. So I would like to show an animation. See, let this be a diamagnetic substances like copper. We applied some external magnetic field in this region and we introduced a diamagnetic substances in that region. Then see, most of the lines, actually these are uniformly distributed. This blue line shows the magnetic field line. Actually these are uniformly distributed. Even in this place of magnetism, there were some magnetic lines. When this diamagnetic substance is introduced in that region, it repels those magnetic lines. They are avoided in this region, they move outside. Because of inducing magnetism inside the diamagnetic substances, that repels the applied magnetism. Okay. So according to definition, I explained the structure. An example from that we are now we are able to understand the first property. Because of inducing magnetism in opposite to the applied field, so magnetic field lines avoid the diamagnetic substance, they move outside. So let us see how the magnetic lines passes in paramagnetism. Here let this be a paramagnetic substance. The magnetic lines, see, so this line bend into the magnet, partially attracted. So these paramagnetic substance partially attracts the magnetic field lines. So they move into the substance, through the substances. Whereas the ferromagnetism shows a strong magnetic property, it attracts the magnetic lines more effectively, so they are crowded. So see that let this be a ferromagnetic substances like iron, a cobalt or nickel, and see, observe the difference in the animation. Here only 3 lines that passes through paramagnetic. Here 1, 2, 3, 4, 5 lines. So they are crowded. It has the nature of attracting more magnetic field lines to pass through it. Hence magnetic field lines are crowded in ferromagnetic substances and passes through it, and whereas dia, they are repelled. They avoid the magnetic field lines. Students, I think you followed this example very well with this animation explanation. Let us move on to the next property of classification. So dia, para, ferro, we are continuing. Here I would like to explain 2 more properties of it. When diamagnetic substances placed in a non-uniform magnetic field, non-uniform means at certain region there is a strong, at certain region there is a weak magnetic field. When diamagnetic substance is placed in non-uniform magnetic field, so let us observe this line. Diamagnet is placed in non-uniform magnetic field means the magnetic strength changes from place to place, a point to point in a particular region. It moves from stronger to weaker. Only reason is diamagnetic substances are the substances which are feebly repelled by the magnet. Repelled means it must move from stronger to weaker. That's why they shifted from stronger to weaker. Whereas the para are the substances which are feebly attracted. That's why they must move in non-uniform magnetic field. They must move from weaker to stronger. So they move from weaker region to stronger region of the field. And same property shown by the ferromagnetic at more effect, more intense. So they also move from weaker to stronger because they are attracted by the magnet. So strong attraction, feebly attraction, strong attraction, that is the difference. But anyhow, para and ferro both are moving in a non-uniform magnetic field from weaker region to stronger region, feebly and strongly, that is the difference. Comes to the one more property. When a diamagnetic rod is feebly suspended in uniform magnetic field, let this be a diamagnetic material such as copper. We suspended this diamagnetic substance in a uniform magnetic field. Now it is repelled by magnetic field so that it comes to perpendicular to the direction of magnetic field. So let us see the animation, students, looking to the image. So see, it is directed perpendicular. So I would like to show one more time. Let this be a diamagnetic substance such as copper. We suspended diamagnetic substance in uniform magnetic field. Externally we apply uniform magnetic field and we suspended diamagnetic material in uniform magnetic field. It is repelled by the magnet so that it aligns perpendicular, it rotates to perpendicular direction of magnetic field. That is the point here. I show, observe this one. I am showing the same property in the animation. So observe it. It comes to perpendicular to the direction of magnetic field. Okay. Whereas paramagnetic substances are attracted by the magnet, feebly attracted, so they must align. If you suspend the paramagnetic in any magnetic field, let this be a paramagnetic. Look into the animation. We suspend the paramagnetic in a magnetic field. It is attracted by the magnet so that it comes to parallel to the direction of magnetic field. We observe same thing in that animation. Okay. Same phenomena also happens in ferromagnetic but with strongly. So it is also when suspended in external magnetic field, so comes to parallel. So you observe it. So it aligns parallel to it like that. So next one more property. Dia, para and ferro. Here if a diamagnetic liquid taken in a watch glass. So let us take a watch glass shown here and this be the diamagnetic material such as copper. If a diamagnetic liquid, now it is in form of a liquid. If diamagnetic liquid is taken in a watch glass, is placed in uniform magnetic field, it collects away from the center. It collects away from the center when magnetic poles are close and collects at the center when magnetic poles are farther. So try to make clear. So it collects away when the magnetic poles are closer. So these two are the important. Collects away when magnetic are closer. So here these magnetic poles are closer. Look into the diagram. Magnetic poles are closer. So what is the property of diamagnetism? It is repelled, feebly repelled. So it gets repelled so that it collects away. Only thing is diamagnetic substances are feebly repelled by the magnet. Because that reason, if a diamagnetic liquid is poured in a watch glass and kept in a magnetic field such that poles are very close to each other, they get reflected, diamagnetic substance get reflected and they move away. Whereas when they collects at the center when magnetic poles are farther. So see the animation here. Okay, like this. Magnetic poles are away from each other, they are at farther distance of separation. Now they are repelled. Diamagnetic is repelled so that they collect at the center. So diamagnetic substance repelled by the magnet is the only property to have this classification. When poles are close, they are move away. When poles are farther, it is collected at the center. The opposite phenomena will happen in para and ferro, because para and ferro are attracted by the external magnetic field. So when para or ferromagnetic liquid is taken in a watch glass, placed in uniform magnetic field, it collects at the center when the magnetic poles are closer, because it is attracted. It is attracted. So paramagnetic as well as ferromagnetic are simply attracted by the external magnetic field. So when magnetic poles are closer, it collects at the center, and when magnetic poles are farther means away, then it collects at outside. So they move away, because it is collected by the magnetic poles. So it moves away. The same thing will happen in ferromagnetic material also, but with more intensity, strongly. So when they are close and they are collected at the center because of attraction. When they are farther, they collected away. They collected by the poles, so that's why liquid moves away than paramagnetic. Same as the ferromagnetic, nothing different, with more strong nature. So let us move on to the one more point of the property of the substances. So dia, para, ferro. This is one more point. When a diamagnetic substance is placed in a magnetic field, it's weakly magnetized in a direction opposite to the inducing field. Opposite to the inducing field. So suppose let this be a copper substance which is a diamagnet. When some external magnetic field is applied over it, so it gets magnetized in opposite direction. It has its magnetic moment feebly. It gets magnetized feebly, partially, lightly in opposite direction. So this becomes the south pole and this becomes the north pole. It gets magnetized feebly but not strongly. See the direction of magnetic moment. So opposite, this is the applied magnetic field. Opposite to the direction of applied magnetic field, the substance get magnetized in opposite direction, partially with some magnetic moment. So when a diamagnetic substances as shown in the diagram placed in a external magnetic field, here this is the external magnetic field, then this substance gets weakly magnetized in direction opposite to the induced field. Okay, next one. Then induced dipole moment is small and negative. Induced dipole moment. So dipole moment is represented by M. It is very, very small amount of magnetic movement get induced diamagnetic opposite to the direction. Hence we are using negative sign. M is negative and a very small amount of M is induced. Suppose the applied value is H, magnetizing force or magnetic intensity and magnetizing field. In previous part of our videos, we clearly described about these definitions. So magnetic intensity or magnetizing field applied is H. Then the magnet get magnetized. The substance, diamagnetic substance get magnetized in very small amount compared to H in opposite direction. Now paramagnetic substances. Let this be the uniform magnetic field in a particular region. We inserted a paramagnetic substance such as aluminum material in applied H. This is the applied H, magnetizing force, magnetic intensity. Then this paramagnetic substances get magnetized, because already I explained that the atoms which were randomly oriented may orient partially along the direction of applied field in paramagnetic substances. When it introduced in external magnetic field, the atoms may orient their magnetic moment along the applied magnetic field. That's why they get a partial magnetic moment. So along the direction of H, this is the direction of H, applied magnetic field. Along direction of H, partially the substance get magnetized. It get magnetic moment. So when paramagnetic substance is placed in a magnetic field, it's weakly magnetized in the direction of inducing field, so that M is positive and very small value. Induced dipole moment, M is small and positive, very small, but positive value because it is along the direction of applied magnetic field. Now if we consider a ferromagnetic substances, students, I already clearly explained it has domain structure. In a domain there are around 10 power 11 atoms which has the magnetic moment along same direction. If such a material is placed in external magnetic field, here this is the external magnetic field. When you insert a ferromagnetic substance such as iron in external magnetic field, all domains orient along the applied magnetic field depending upon temperature. All domains orient along the applied magnetic field and it gives a strong magnetic moment. The substance gets magnetized. Once all the dipoles of the atoms contributed by the substance, all the domains of the atoms in a substance orients along the applied magnetic field, the vector sum of magnetic moments becomes a large value. So it gets large magnetic moment along the applied magnetic field. So that when a ferromagnetic substance is placed in a magnetic field, it is strongly magnetized in the direction of the inducing field. So induced dipole moment M is large and positive. So let us move on to the next point of the classification. So that the intensity of magnetization, so students, the expression for intensity of magnetization is magnetic moment per unit volume. This is the formula. Intensity of magnetization is the magnetic moment induced in a material per unit volume. Magnetic moment per unit volume is intensity of magnetization. As magnetic moment is negative, hence intensity of magnetization has a small and negative. We know that magnetic moment is small and negative, so that intensity of magnetization developed inside any diamagnetic substance also small and negative. And in paramagnetic substance, magnetic moment is small and positive, so that the intensity of magnetization is also small and positive. We know that in ferromagnetic material, the magnetic moment is large and positive. Hence, as intensity of magnetization is magnetic moment per unit volume, here intensity of magnetization also large and positive. So next one, magnetic relative permeability. Relative permeability is always less than unity and positive. So I would like to explain this point after the explanation of susceptibility. So you may understood relative permeability value more effectively after knowing the value of susceptibility. So let us move on to the susceptibility value. So I would like to first explain magnetic susceptibility. Students, magnetic susceptibility, Zm, is the ratio of intensity of magnetization to the magnetizing field. Susceptibility is a parameter to know about the magnetic strength, magnetic property of a magnetic material. It is the ratio of intensity of magnetization to the magnetizing field. We know that intensity of magnetization is small and negative, so that susceptibility also small and negative. It is in negative decimal. You may understand it more effectively in this manner. It may be in negative decimal because I is less than H. Here I is less than H and negative in opposite direction. I is less than H, I is opposite to H. That's why you get negative decimal value, small and negative. Whereas here I is less than H and positive along H. Intensity of magnetization, magnetic moment per unit volume is less than applied magnetic field, magnetizing field. I is less than H but positive. So that Xi is equal to I by H. I is less than H in paramagnetic, so that you get positive decimal. In that way you understood. A small positive value means it may be in the positive decimal, like 0.1, 0.2, 0.03. it may be positive decimal, whereas in dia it may be negative decimal, minus 0.1, minus 0.5, like that. Ferromagnetic, magnetic susceptibility, so I is greater than H. Intensity of magnetization, due to orientation of domains along the applied magnetic field, intensity of magnetization is large in value. Relatively, it is greater than H and along H. I is greater than H and along H direction. Therefore, susceptibility is large. It may be in the order of 1000. It may be in the order of 1000. It is in the order of just a decimal. But whereas ferromagnetism, induced intensity of magnetization is more than the applied magnetism. That's why magnetizing field. That's why I is very greater than H. Greater than H means it is approximately 1000 times more than the H value. I is 1000 times more than the H value for iron, copper, iron, cobalt, nickel. So that we are getting the susceptibility value is also in the order of 1000. So let us move on to the relative permeability now. So relative permeability, mu r, relative permeability is equivalent to 1 plus Z. We have this relation, 1 plus Z. Already I explained very clearly for diamagnetic substances, the Xi value for diamagnetic substances, the Xi value is negative decimal. When negative decimal value is added to 1, it becomes positive decimal. That's why positive decimal means the magnetic relative permeability is always less than 1. Positive decimal, that is the meaning. It lies between 0 and 1. 0 less than mu r less than 1. Positive decimal. Xi is negative decimal added to 1. So we get positive decimal. That's why it is always less than 1. Relative permeability. And the magnetic relative permeability is more than 1. Because Xi is positive decimal. Xi is positive decimal. So mu r is equal to 1 plus some positive decimal like 0.1 like this. It may becomes 1.1. For example, I am giving this numerical value to have good clarity. That's why it must be greater than 1. We are adding positive decimal to the 1 to find relative permeability. That's why the relative permeability must be slightly greater than 1. Slightly greater than 1. Already explained that the Xi value is around 1000. That's why mu r is very greater than 1. Mu r value is also in the order of 1000 for iron, cobalt, nickel, like that. Xi is very greater than 1 in the order of 1000. Then obviously mu r also greater than very greater than 1 in the order of 1000. Okay. Next, move on to the next classification. I already explained about susceptibility. Then diamagnetic substances, they do not obey Curie's law. So in next slide I explain about the Curie's law. They do not obey Curie's law. Their properties do not change with temperature. So diamagnetism, how magnetic property, that is susceptibility. The relation between susceptibility of a substance and temperature is explained in the Curie's law. We will discuss in the next slide in a moment. So Curie's law is an equation that relates susceptibility of a substance with temperature. How magnetic susceptibility varies with temperature is given in Curie's law. Here almost diamagnetic substances, its diamagnetic property almost unaltered, which is feebly repelled by the magnet, which induces a partial magnetic movement opposite to the applied magnetic field. That is the diamagnetic property, and it does not depends upon temperature. It remains in form of diamagnetic every time for any temperature. So diamagnetic property or diamagnetic substances does not obey Curie's law, which explains a relation between susceptibility and temperature. Whereas the paramagnetic substances, they obey Curie's law, they lose their magnetic property with rise in temperature. So in Curie's law, there is an inversely proportional relation between susceptibility and temperature. So that as temperature of the paramagnetic substances goes on increasing, the susceptibility of, susceptibility is a numerical value, shows the magnetic property. So magnetic property of paramagnetic substances goes on decreasing with rising temperature. That property clearly followed Curie's law. This is Curie's law, that clearly followed by paramagnetic substances. Whereas ferromagnetic substances, which shows a strong magnetic property, behaves like ferromagnetic substance up to certain temperature. Above certain temperature, there is a critical temperature for every ferromagnetic substances. There is a critical temperature for every ferromagnetic substances at which they transform their nature to paramagnetic substances. Because the disturb due to disorderness produced in ferromagnetic substances at high temperatures, above certain temperature of a ferromagnetic substances, it destroys the domain nature and simply becomes the paramagnetic nature. So, in case of ferromagnetic substances, they obey Curie's law at certain temperature called Curie point. Because at Curie point, it changes to paramagnetic and follows the Curie's law. At critical temperature, every ferromagnetic substance has its own Curie temperature, at which it clearly changes its nature from ferromagnetic to paramagnetic substances. Thereafter, it follows the Curie's law. So, next, these are the explanations of the classification of magnetic material into three categories: dia, para and ferromagnetic substances. Let us know about the Curie's law, that is the very important law for paramagnetic substances, and also we would like to know about what is Curie temperature. These are the two important things to be discussed more clearly to understand this last property. So let us move on to the Curie's law. So this is the important law. You have numericals problems in all textbooks belongs to the Curie's law. Here Curie's law is a law applicable clearly for paramagnetic substances. Curie's law is applicable for paramagnetic substances. So Curie's law, one more thing, gives the relation between susceptibility and absolute temperature of paramagnetic substances. First, try to clear what is the relation given in Curie's law. Curie's law belongs to paramagnetic substance. This law gives a clear relation between susceptibility, that is I by H, which is used to measure the magnetic property of a material. So it gives a clear relation between susceptibility and absolute temperature of paramagnetic substances. So let us come to the statement of Curie's law. Magnetic susceptibility, that is Zi, of a paramagnetic material varies inversely with absolute temperature. Very simple relation. So we know that the I proportional to H. If you have a paramagnetic substance, let us consider a paramagnetic substance and applied external magnetic field in it, then magnetic movement partially developed along the direction. This is a H value, this is magnetic movement. Then I is equal to m by v, I value. Magnetic movement per unit volume is intensity of magnetization. I induced inside the paramagnetic material along H. So this I proportional to H. As H increases, I also get increasing. When you increase the applied magnetizing field on a paramagnetic material, the orientation of atoms along the direction of applied magnetic field increases. So H increases, M increases, I increases. So I proportional to H. The intensity of magnetization induced inside a magnetic material caused by H, so I proportional to H. And one more important point is I is inversely proportional to T, absolute temperature. If absolute temperature of magnetic material increases, then they got thermal energy. The random motion of the atoms get increased, they becomes disorder and it destroys the contribution of magnetic momentum. So magnetic momentum goes on decreasing as absolute temperature increases. According to this explanation, as absolute temperature increases, the substance get thermal energy. So random motion of atoms increases. They get oriented along different directions. That reduces the magnetic movement and also reduces the intensity of magnetization. So they are inversely proportional. Absolute temperature and I value are inversely proportional. So intensity of magnetization is inversely proportional to absolute temperature of magnetic substances. Then on cross multiplying, I by H proportional to 1 by T, I by H. We know that ratio of intensity of magnetization to the magnetizing field is susceptibility. So that susceptibility of a magnetic material is inversely proportional to absolute temperature. This is the basic relation of Curie's law. For a paramagnetic substance, the susceptibility of it is inversely proportional to absolute temperature of the material. As this clearly shows, if absolute temperature of paramagnetic substance goes on increasing, susceptibility decreasing. It means magnetic property decreasing. So magnetic property of paramagnetic material is inversely proportional to absolute temperature. It depends upon temperature in inversely proportional relation. So we introduce a proportionality constant C. So xi m is equal to C by T. This is the ultimate form of Curie's law. Equation form of Curie's law for a paramagnetic substance. Susceptibility is equal to C divided by capital T. Xi m is the susceptibility of paramagnetic substance. C is Curie constant. We introduced C value, Curie constant. T is absolute temperature of the material. So for ferromagnetic material, the same formula modified as shown here. Xi m is equal to C by T minus Tc. Here, as long as it is in form of ferromagnetic material, there is no change in its magnetic susceptibility. As long as substance is in the form of ferromagnetic material, there is no fall or change in the value of susceptibility. It remains unaltered. It has its own susceptibility value around 1000, generally ferromagnetic material. If the temperature goes on increasing, definitely at a particular temperature, for all rise of temperature, it doesn't changes its nature. Student, remember, for every rise in temperature of a ferromagnetic material, its property of susceptibility, its value of susceptibility may not changes. But the temperature goes on increases. Definitely there is a limit for the temperature value at a particular temperature, that is critical temperature Tc. At a particular temperature known as critical temperature denoted by Tc, the domain structure get destroyed. The domain structure of ferromagnetic material get destroyed and transferred to, once domain structure get destroyed, it transfers to paramagnetic material. So that at a particular temperature known as critical temperature, the domain structure of the ferromagnetic material get destroyed and simply it transfers to paramagnetic material. So critical temperature is the temperature of a ferromagnetic material at which ferromagnetic material changes to paramagnetic material. Okay, that is about Tc. Then once it comes to paramagnetic material, this relation holds good. So this relation holds good after the conversion of ferromagnetic to paramagnetic. Then xi m is equal to C by T minus Tc. This is valid when T is greater than Tc. Once T is greater than Tc, ferromagnetic material transforms to paramagnetic material and it holds good. So here Curie temperature is the temperature at which domain structure of ferromagnetic material get destroyed and transforms to paramagnetic material. Thereafter the susceptibility goes on reducing with rise of temperature above Curie temperature. So Curie temperature is not constant for all ferromagnetic material. It changes from material to material. Each and every ferromagnetic material has its own Curie temperature. Curie temperature for iron is 1000 Kelvin, around 1000 Kelvin. For cobalt around 1400 Kelvin, and for nickel it is 600 Kelvin. So at this temperature 1000 Kelvin, its meaning is iron changes from ferromagnetic to paramagnetic, but it is too high temperature. We are at room temperature, we are living at room temperature around 300 Kelvin. But that is 1000 Kelvin, that very high temperatures it transforms to this one. Similarly, cobalt 1400, it is more than the iron temperature. Like that, that's why generally if you consider iron, it retains its ferromagnetic nature for available temperature, for useful temperature. So this is about the Curie's law. And students, we are going to discuss one more important, very important phenomena of magnetism. With this we come to end of theory part of the magnetism and matter. In further video, next video, we go for the numericals. But in this video, I would like to discuss one more important property, phenomena of magnetism, that is hysteresis loop of magnetization curve, hysteresis loop. So in this image, you are observing that the hysteresis loop, only one thing, the hysteresis loop shows the variation of B or I. I means the intensity of magnetization. How the intensity of magnetization varies with applied magnetic field. So this is magnetizing force. How the magnetic flux density or intensity of magnetization, because B is related to I increases, B is also increases. Of course, the relation is, we know that B is equal to mu naught into I plus H. H is constant, H is the applied value. If I increases, B also get increases. So hysteresis loop shows the variation of intensity of magnetization or magnetic field flux density through the given material. How the B or I of a material is changing with H value in one cycle. We increase H value and we reduce H value and we change the H value to negative and we change the H value to positive. We oscillate H. We are applying a positive and negative and positive. So we apply an oscillating magnetizing field, also known as magnetic intensity, also known as the magnetic force. We apply oscillating, means positive, 0, negative, 0 and positive. This is known as the oscillating value. We apply a oscillating magnetizing force on a material and we observe how the B or I, magnetic flux density or intensity of magnetization, vary for oscillating magnetizing force. That will be drawn in form of a graph known as the hysteresis loop that explains about the application of that particular ferromagnetic material. This is only drawn for ferromagnetic material. The variation of B and I with oscillating H is drawn and we understand the property of the ferromagnetic material with the help of hysteresis loop. So let us move on for the explanation. To draw hysteresis loop, we apply a oscillating magnetizing field. The applied magnetizing field on any ferromagnetic material is taken along x-axis and I or sometimes B, whatever it may be. B is related to I. Mu naught of I plus H is B. When I changes, B changes. That is the only nature. So how the intensity of magnetization or magnetic field density through the material varies, that induced in a material is taken, induced value effect is taken along the y-axis, applied value is taken along the x-axis to plot hysteresis loop of or magnetization curve of a ferromagnetic material. So as H increases, first of all we consider a magnetic material like iron, such as iron, ferromagnetic material. Let this be a ferromagnetic material such as iron and we apply, let this be a solenoid. When you allow the current to pass through the solenoid, magnetic field is applied. The H acting is Ni. B is mu naught Ni. You know that B is mu naught Ni. Already we have a clear idea about magnetic field along the axis of solenoid. then magnetizing force is B by mu naught, so Ni, where N are the number of turns per unit length, I is the current passing through the solenoid, as I varies, H varies. So simply we vary the H value very simply by changing the current through the solenoid, we change the H value. So we gradually change the H either to positive or negative values by changing the direction of current and magnitude of current. H is equal to Ni. This is this shaded one is magnetic material. We inserted this magnetic material inside the solenoid and we apply H and we observe how the I value is changing with H. As H increases, increase I so that H increases. As H increases in ferromagnetic material, all domains with increasing H, all domains try to orient along same direction and gives a large amount of magnetic moment, so that intensity of magnetization. So when H increases, see the graph. In this manner, in this way, I also increases. When H is 0, I may be 0 because random oriented directions of domains. When H applied, magnetizing force applied on the magnetic material increases in positive magnitude, positive value increases, I also get increased as shown in the diagram. Then it reaches a saturation. Once all the domains get oriented, along the direction of H, no possibility to get extra value beyond that. So that is said to be a saturation value. The value of I at which all the domains get oriented along the applied H value, that is said to be saturation value. The magnet gets saturated at particular value of H. Definitely magnet gets saturated at particular value of H. Then we decrease the H value. Suppose if you decrease I value, H is also goes on decreasing. That is very simple. So we decrease the H value by decreasing current passing through the solenoid. Then when we decrease the H value, I gradually decreases. I will explain the shape more clearly. Okay, this is the shape. Let me to describe the change of I with H in step by step. Let this be the first step. Intensity of magnetization, I increases with increasing magnetizing force. That is known thing for ferromagnetic material. I increases with H. Initially through OA and reaches saturation at A. So that's what I explained already. As H increases, domains get oriented along the direction of H and I also get increases. At one value of H, at a particular value of H, all the domains get oriented along the H direction and it get completely magnetized. That is the saturation value. The magnet reaches the saturation value. Then what we do? We decrease H by reducing I. So when H is decreased, once we are coming back along negative x-axis, we come back to 0. So we reduce H value. Next step, after reaching the saturation A, we reduce H value by decreasing current through the solenoid. Then I also get reduced. This is the graph. When you reduces H value to 0, I also get reduced. Okay. Let us observe the area at which I am plotting the graph here. When H goes on decreasing to 0, I goes on decreasing. But the very, very important point is I doesn't becomes 0. Though H reduces to 0 in ferromagnetic material, I doesn't reaches a 0. Once after getting saturation, even though we reduces H to 0, but I can't become 0. The intensity permanently present inside the ferromagnetic material to some extent. So it becomes a permanent magnet. So it retains its magnetic property. The ferromagnetic material retains its magnetic property to some extent. This is that extent value. Even though we completely remove the applied magnetizing force. Understood it carefully. So when H decreased, I decreases, but it does not comes to 0 at H is equal to. This is a sharp point line to understand the nature. When H is decreased, I decreases, but it does not come to 0 at H is equal to 0. It shows that the ferromagnetic material becomes a permanent magnet. It retains its magnetic property to some extent, even though we completely eliminated the applied magnetizing force. That is the important point. Then we apply the magnetizing force in negative value. The residual magnetism, now this is the important line. This is the important line. The residual magnetism set up in the material represented by OB called retentivity. When applied magnetizing force reduces to 0, the remaining value of the magnetism, that is magnetic field, inside the material, when H reduces to 0, the remaining value of magnetic field intensity inside the material is known as retentivity. Okay, then to bring I to 0, we would like to bring I to 0. At H0, I can't become 0. So to bring I to 0, we must apply the current in opposite direction. We flow the current in opposite direction so that now the H is applying in negative x-axis. See the direction. Now we are increasing the H value in negative direction. To bring I to 0, to demagnetize completely, that is the meaning, to demagnetize the substance completely, opposite negative magnetizing force is applied. Negative magnetizing. We applied the magnetizing force in negative x-axis. This magnetizing force represented by OC called coercivity. When you increase the magnetizing force in negative value, definitely at certain negative value the magnetic field or intensity of magnetization of a magnet, ferromagnet, becomes 0 at certain negative value of magnetizing force. That negative value of magnetizing force is represented by OC. This OC is known as coercivity. The negative value of applied magnetizing force to bring the intensity of magnetization of the magnetic material to 0 is known as coercivity. Then we increase the magnetizing force in negative direction, it reaches the saturation. After reaching the saturation level D, we reach the saturation. When the magnetizing force is reversed, from this onwards, once again we apply magnetizing force in positive direction, the intensity of magnetization changes along the direction of DEFA for the cycle. So after reaching the saturation level D, here when the magnetizing force is reversed at point D, we start the reverse direction. The curve close to the point A, completing a cycle. So here this cycle is completed by applying the oscillating positive, 0, negative, 0 and positive H value. The loop AB, CD, EFA is called hysteresis loop. So this AB, CD, EFA is known as hysteresis loop. The area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization. So area of the loop, clearly when area of loop means we take the product of H and B or H and I. This product has units of energy. So because of this, the loop, area of the loop clearly shows the loss of energy. When this magnetic substances undergoes a cycle under applied H value, positive, 0, negative, 0, positive, this is cycle. When magnetic material undergoes a cycle for applied H value, the area of the loop of A, B, C, D, E, F, A, this area of the loop shows the loss of energy. So the area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization, and it is dissipated in form of heat. This is the important point. So area shows during magnetization and demagnetization, area of the loop shows the loss of energy, that is in form of heat energy. Okay. The material like iron having thin loop. So here we would like to give a clarity. Which ferromagnetic material are useful to prepare permanent magnets and which magnetic material are used to prepare electromagnets? Ferromagnetic material may be used in two ways. Some materials are used to prepare permanent magnets. Some materials are used to prepare permanent magnets. The material for which area of the loop is less, the material, ferromagnetic material for which area of the loop is less, they are used for electromagnets. I repeat, the material for which area of the loop is less and coercivity is less, retentivity is less, the material for which coercivity and retentivity is less, they get magnetized in the presence of H and they get easily demagnetized. If area of the loop is less, coercivity is less, retentivity is less, they get magnetized by the applied magnetic field, and also by removing applied magnetic field they get demagnetized very easily. So getting magnetism and getting demagnetism is very important for preparing electromagnets. In the presence of passing the current through the solenoid, they get magnetism. When you remove the current, they get demagnetized. This is electromagnet. So in the preparation of electromagnetic, the area of the loop must be small so that it get magnetized as well as demagnetized very easily by the applied field and removing field respectively. Hence, soft iron is the material. Soft iron is the very good ferromagnetic material which has less area of the loop, which is very much useful to prepare electromagnets. Therefore, the material like iron having thin loop is used for making temporary magnets. That means electromagnets. Other name for temporary magnets is electromagnets. And the material for which the retentivity is high, remaining amount of magnetic field when applied magnetic field reduces to zero is retentivity. The material for which retentivity is high, materials for which retentivity is high are used to prepare permanent magnets. Even though we eliminated applied magnetic field, they retain its magnetic property to the large value. If coercivity is high, what is its meaning? Even though we completely removed the applied magnetic force, it retains its magnetic property to high value. Hence, it becomes a permanent magnet forever and ever. Hence, it is used as the permanent magnet. Steel shows that property. That's why the steel is used for permanent magnets. The loop area is small. For iron, they are used to prepare the electromagnets known as temporary magnets. Steel is a material, ferromagnetic material, which has large area of the loop and which shows large value of retentivity and coercivity. It retains its magnetism for a long time even in the absence of applied magnetic field. Hence, they are used to prepare permanent magnets. So, I conclude this explanation. Here in this animation, you are observing for some ferromagnetics area is large, for some magnetics area is less. For steel, this is large. For iron, you are observing this is for iron. Now, this is for steel. Next, this is for iron. Iron has less area, steel has more area. Hence, steel is used to prepare permanent magnets. Soft iron is used to prepare temporary magnets known as electromagnets. Here I shows it very clearly. Here the loop area is less. Hysteresis loop area is less for soft iron. This is the hysteresis loop of soft iron whose area is less. Hence, they are used to prepare temporary magnets. They are used in transformers. In the preparation of transformers, we must use the core. The core of the transformer is made up of soft iron. Core of the transformer is made up of soft iron because it undergoes so many cycles of increasing and decreasing H value. The core of the transformer undergoes so many cycles of increasing and decreasing H value. Then to have minimum loss of heat, to have minimum loss of energy in form of heat, the area of the loop must be small. As soft iron has less area of the hysteresis loop, they are used as the cores of the transformer to reduce the loss of heat. Similarly, area of the loop is large for steel, so they are used to prepare permanent magnets. as shown in the diagram. Students, I hope you followed the explanation of the very important discussion. Students, in this video, most probably we discussed only about theoretical description with the help of animations and classifications and images and videos. I explained the classification of magnetic material into three properties, that is dia, para and ferro, and hysteresis loop, and how it is useful to prepare permanent magnets and temporary magnets explained in this video. I hope you followed it very well. Thank you for watching. Thank you very much.